Welcome to Chapter 7. We're going to lead off with area between curves. And it's either going to be top function minus bottom function that you integrate, or if the curves are sideways, and we'll see a couple like that, you go right minus left. If you think about the way that you graph numbers, going up and going to the right make the values larger. You know, when you go up on the y-axis or when you go to the right on the x-axis. So really both of these formulas are saying large minus small. Top minus bottom, right minus left, large minus small. Okay. In Chapter 4, we noticed that the area can be denoted with an integral. The thing about Chapter 4, however, is every shape that I drew had a bottom boundary of the x-axis. And when we checked it on the calculator, it had the calculator color in the region. The calculator is trained or programmed to color down to the x-axis and stop. So we really didn't have full functionality that we're going to have now in Chapter 7. In Chapter 7, you're going to have drawings that go across the x-axis, or the two curves are going to cross in strange places, and we'll still have to find the areas of the regions they make. So this is a little bit more advanced than what we saw earlier in Chapter 4, but not too terribly hard. All right, enough of me talking. Let's get to example number 1. Find the area between the curve, y equals 1/2 x squared plus 2x minus 7, which is going to be an upward opening parabola, and y equals 5 plus x, which is a line. The most important thing that you can do for yourself is to make a good, solid, careful, accurate graph. Because if your graphs aren't accurate, the curves aren't going to cross at the right places. If the curves cross at the wrong places, you're going to be using the wrong limits of integration when you try to integrate, which is going to ruin your answers, of course. So I'm going to carefully graph these and color or shade the region in between them. Okay, the curve is in blue, the line's in green, and they happen to cross at the points 4, 9, and -6, -1. If you're not sure if that's where they cross, you can always try one of the points in. For example, the 4, 9. If I try that in, the line obviously goes through there. You can see that 9 is 5 plus 4. And the blue curve, 1/2 of 16, that'd be 8, plus another 8 minus 7, that's also 9. So, you can verify it. You can also put the -6, -1 in. They do cross at those places. In the event that you weren't allowed to have a calculator, what you would just do is simply set the green and blue equations equal to each other and solve using either factoring or quadratic formula, and you would find that x comes out to be 4 and x comes out to be -6, and then you can just get the y-coordinates by plugging it into one of the equations. I'd probably plug into the green would be much easier. All right, regardless, you can see that we have this yellow shape, and we need to find the area of it. If I just look at the blocks, there are quite a few blocks shaded there. Obviously, if we get an answer of 5, we know it's way too small, but if we get an answer of 1,000, it's way too large. So, at least reasonably, we can kind of estimate that, I don't know, the answer looks to be somewhere between maybe 60 and 100. And again, I'm not going to count them all, but somewhere in that range. All right, let's see what we can do. The formula says area is either top minus bottom or right minus left. In this case, it's going to be top minus bottom. It's going to be green minus blue. And I start at -6, and I go green minus blue. Green minus blue. It's almost like we have a whole bunch of skinny rectangles, like we were doing the LRAM, RRAM, MRAM, or even trapezoidal rule. And these rectangles work their way across the shape. Top minus bottom. Notice every single time I'm starting from the green, I'm ending at the blue, and I'm hitting both of them. Top minus bottom. And this phenomenon ends when I finally reach x equals 4 and the rectangles stop. So the area between the curves is going to be, of course, an integral from -6 to +4. And since those are x limits, I'm going to have a dx way at the end here. And it's top minus bottom, and that'll be it. Now, if you're allowed to use your calculator, by all means, just plug that in, go to Math 9, FNN, and let it solve it for you. All right, just get the answer right away. And the answer in this case is going to be 88 1/3 units, square units, I should say, or 250 thirds. Let's cover ourselves just in case we're not allowed to use a calculator. I imagine we would be on something like this, however. So I can go ahead and simplify and combine some like terms. Keep in mind that this red minus is going to distribute through, giving us negative 1/2 x squared, minus 2x, but here's a plus 1x, so that'd be minus 1x. This negative times negative here will be a plus 7. There's also a plus 5, so that'll make plus 12 dx. Okay, and again, we have not integrated yet, so we're going to go from negative 6 to 4. Up by a power, divide by the new power. And you would have that. And then plugging in the 4 followed by the negative 6. The 4 getting plugged in would give you 88 thirds. Obviously, I'm saving a little time here. Minus, this is fundamental theorem, plugging in the negative 6 will give you a negative 54. Obviously, plus plus, you can get a common denominator. The 54 can change into 162 thirds, and adding these two together will give you the 250 thirds. Square units? Right, so it's about 88 blocks, 88 1/3. That seems reasonable to me. So that's the exact area. The thing about your graphing calculator is it won't help you. If you try to graph this and color it, it usually only colors to the x-axis. You get that thing and you're like, well, what about the rest of it? And so it's not like chapter 4 where it's quite as helpful. All right, number 2, we're going to find the area between the sideways curve, or sideways sleeping parabola, x equals 11 minus y squared, and the line x equals 2y plus 3. Ugh. All right, graph them carefully, which I did, and then we shade the region in. Again, if you're not sure where they cross, you can always set them equal to each other. I think I'll actually do the algebra this time to show you that. All right, set the equations equal. Take away 11 from both sides. Add y squared to both sides. The goal is to get a 0 on the right. That gives us y squared plus 2y minus 8 equals 0. And that'll factor into y plus 4, y minus 2. So y is either going to be negative 4 or y will be positive 2. And you can see that that is where they intersect. There's the y is negative 4. Here's the y is positive 2. And if you plug those numbers back into either one of these, it doesn't matter which one, you'll come up with the x coordinates of the negative 5 and the 7. All right, so anyway, we have the border points. Now, we cannot do what we did in number 1. We can't go top minus bottom. And the reason why is because once we get to this 0.72, we're going to have an issue. Check this out. Green minus blue, green minus blue, green minus blue, top minus bottom. And that's totally fine all the way from negative 5 to 7. But once you hit 7, it's no longer green minus blue, it's blue minus blue, which blue minus blue is not going to help us. You can't go from yourself to yourself. So we can't go in that direction. We have to go sideways. Plus, if it wasn't obvious already that we're going sideways, we have equations that are x equals, which is kind of a dead giveaway. So let me flip these rectangles around, and we'll go right minus left, which will be blue minus green every time. We start at the bottom, and we go right minus left. Right minus left. Blue minus green. blue minus green. And that goes all the way from y equals -4 up to y equals 2, blue minus green, right minus left, until they meet. That'll give us the proper area of that yellow shaded region. Since the rectangles are sideways and I'm going right minus left, it's not going to be dx at the end, it's going to be dy. And we have y limits, not x's. Notice that the limits of integration, I didn't use the -5 and the 7. I used the -4 and the 2. And right minus left in this case means blue minus green is going to get integrated. As always, we have a distributive property going. So those will both become negatives. If we combine the like terms, we'll have -y squared minus 2y plus 8. 11 minus 3, that's plus 8. Integrating this will be -1/3 y cubed minus y squared plus 8y. Plugging in the positive 2 and working that out will come out to 28/3. The -4 plugged in will give us -80/3. Again, I'm saving a lot of time just by not showing all the details here. That's going to be plus. And that'll make 108/3. Although 108 does divide by 3 evenly, I know the digits add up to 9, so it should. And 108 divided by 3 happens to be 36. Now I just take a moment to stare at my picture. I'm like, is that a reasonable answer? 36 blocks being colored in? It looks to be true. I mean, it's obviously not way off, so I feel pretty good about that answer. And 36 square units does, in fact, happen to be the correct answer here. All right, let's check out number 3. Number 3 says find the area between that curve, which is a cubic, and the x-axis. So again, a picture that's accurate is most important. You can see that there are 2 separate yellow regions, and we saw this a little bit in chapter 4, how one region's below the x-axis, and when you integrate that, it's going to turn negative. And we want area, the directions say area, so we have to make sure that that doesn't become negative or it's going to take away from the stuff that's above the x-axis, which is also much larger, as you can see, so we can't use symmetry either. We can't just multiply by 2 like we did on some chapter 4 problems. So we're going to set up the integral. Each time, obviously, it's going to be top minus bottom. We cannot go sideways. Not that we'd want to, but if you went sideways, you'd be getting blue minus blue, which is not cool. The most efficient way to do this would be to integrate from -2 to 0, but put a negative in front of that integral. And then integrate from 0 to 4, but leave that positive. And we'll go blue minus green both times. Again, between -2 and 0, it really should be green minus blue. But I went ahead and put the negative in front and switched the order of these 2 around. That makes up for it. Also makes up for the fact that it's underneath the x-axis. When you work this out, you're going to integrate, and it's going to become -1/4 x to the 4th plus 2/3 x to the 3rd plus 4x squared. All right, if you put the 0 and the -2 into the first one, obviously the 0 will give you 0. The -2 will give you 20/3. And of course, 0 minus 20/3 is -20/3, or -6 2/3. And you know what? That is -6 2/3 blocks. It's negative because it's below the x-axis. Luckily, we put a minus in front to trick it into being positive 20/3, so it wouldn't fight the other region. Speaking of the other region, we have to put a 4 in. We go minus, we put a 0 in. I already know that 0 is going to be 0. When you put the 4 in, you get 128/3. which is, 42 and 2/3, and that seems more reasonable for this. It's a lot bigger than the negative 6 and 2/3. All right, so we have positive 20/3 plus positive 128/3. That's going to be 148/3, or 49 1/3 square units. And that's the correct answer for the area between that curve and the x-axis, combined area. All right, now there's one more thing I should tell you, and that is if you are allowed to use a calculator, if you're allowed to use a calculator, the problem becomes much easier. You can simply take the absolute value of the cubic, go straight through from -2 to 4, just plow straight through. Because you're doing the absolute value here, what it'll do is it'll take this negative graph and flip it up. It'll leave the positive graph above the x-axis. It'll just take you directly to the answer instead of you having to fumble around with chopping up the different regions. So that's number 3. Number 4, find the area of the first quadrant region. That means that you're bounded by the x and y axis. And also you're bounded above by that square root curve, y equals x, or rad x, you can see it in red. And you're bounded below by, of course, the x-axis being in first quadrant there, and also bounded below by that green line, y equals 2x minus 6. All right, so we're describing that yellow region. Sometimes the toughest part is to read that paragraph and come up with the drawing that I just made. Sometimes that can be challenging. And if you don't have the correct region, you're not going to get the correct area, of course. Now, the reason I made this problem, and we're going to solve this problem 3 different times. It won't be as boring as that probably sounds. But I want to show you that you have some flexibility here. In fact, there's at least 3 different ways to do this. I think my first plan of attack will be to go top minus bottom. I'll start here at x equals 0, and when I go top minus bottom, it's just going to be red minus 0, red minus x-axis, top minus bottom, until I get to here. And then it's not red minus 0 anymore. It becomes red minus green the rest of the way for that last block. Okay, so that's what I'm talking about. And then we'll just integrate each one of those separately and add them together. All right, there's the integration. If you do first fundamental theorem, if you plug the 3 in, 3 to the 3 halves will be rad 3 times rad 3 times rad 3. That's 3 rad 3 times 2/3. The 3's will cancel out, giving you simply 2 rad 3. I won't bother plugging the 0 in because you can see that's going to be a 0. All right, plus in goes the 4. Well, rad 4 times rad 4 times rad 4 is really just 2 times 2 times 2. That's 8. 8 times the 2/3 in front would be 16/3. Minus 16 plus 24. Again, this is first fundamental theorem, sorry. Plugging the 3 in. Oh, this is going to be beautiful. It was 2 rad 3 before. It's going to be 2 rad 3 again. But luckily, this distributive property is going to happen. So those 2 rad 3's are going to cancel. That's awesome. All right. Minus 9 plus 18. Again, distributive property comes through. So let's see what we have here in our second part. All right, I've got minus 2 rad 3, which is fabulous because those cancel. All right, I've got a plus 9, and I have a minus 18. That's going to combine to make minus 9. These 2 here are going to combine to make plus 8. And then I have a 16/3, which is 5 1/3. So it's really 5 1/3 minus 1. The answer here is 4 1/3, or 13/3 square units. And to be honest, that looks about right. If I was to count the blocks and cut them up with scissors and place them, tape them on there, it'd be a little over 4 blocks. All right, so that's one way to do number 4. Let's try a different way. Of course, what's cool is we already know the answer is 4 1/3, so let me just put that up in the corner to remind myself. What if we go sideways instead? I know going sideways usually isn't the ultimate thing to do because you have x equals, but you also only have one thing to integrate because you're going to be going right minus left, green minus red the whole time, and you're integrating from 0 to 2, which isn't too bad either, so let's try that out. Of course, before I start, I have to rewrite these equations, so in terms of x, this would be x equals y squared, if I just square both sides. So that'll be one thing. And that's the red curve. Let me go ahead and change that to red so I'm not confused later. Yeah, that's better. And then if I get x by itself here, by adding 6 to both sides and dividing by 2, I get, well, obviously x equals y plus 6 over 2. All right, now I'm ready to integrate. The area is going to be the integral from 0 to 2. Remember, 0 and 2 are y limits, so I'm going to have a dy way at the end. You never, ever, ever want to mix x's and y's together. You never want to mix any variables together when you're integrating. It's either all x's and dx's and x limits, or it's all, like in this case, y's, dy's, and y limits. Don't mix. All right, going sideways, it's right minus left, which is green minus red. So green gets to go first. As I put this green in, I'm going to call it 1/2 y. I'm just going to rewrite it. Plus 6/2, which is plus 3. That'll be easier to integrate. So green minus red. And again, notice that they're all y's and dy's. So it's exactly what we'd want. And that parentheses, that first parentheses isn't really doing anything. It's just in the way, so just ignore it. All right, let's integrate. Up by a power, divide by the new power. You're going to have 1/4 y squared plus 3y minus 1/3 y cubed. And like I said, we're going from 0 to 2. So obviously the 0 is not going to matter. That's pretty awesome. Let's go ahead and put the 2 in. 2 squared is 4. 1/4 of that will be 1. Plus 3 times 2, plus 6. 2 cubed is 8, minus 8/3. And obviously the 0 would go into all 3, but it doesn't matter. All right, so we have 7. What is 7? 21/3, right? Okay, so we have 21/3, or 7, minus 8/3. And you know what 21 minus 8 is? It's 13/3. All right, so that was a much easier way to do it. So normally you don't want to turn things sideways, but once in a while it's kind of nice. All right, let's try number 4 again, just one more time with a different method, just to see some flexibility that we have. Again, we already know that the answer is going to be 13/3, or 4 1/3 square units. This time around, maybe we ought to just ignore the green for a second and just go with the red. And what I mean by that is just go red minus x-axis, red minus 0, red minus 0. And just keep going red minus 0 all the way to here. And then what will happen is you will have counted a triangle that was white and was not yellow, and you would have counted it, so then you have to subtract off that white triangle right here. I think that's going to be kind of cool. Let's try that out. So this time the area is going to be integrated from 0 all the way to 4. And it's just going to be the square root of x, which is, again, the red function. But this time it's minus 0, minus the x-axis, which I'm not going to write. And that's going to make our answer too large. Again, we're counting this blue triangle with white inside that we should not be counting, so we just have to take that away. Take away that triangle when we're done. Actually, the area of that triangle is just going to be 1 block, so just go minus 1 off of our answer. And this is super easy to integrate. It's already x to the 1/2, so when you integrate it, it's going to become, as we've already seen, 2/3 x to the 3/2. Again, I'll leave the 2/3 out. 4 to the 3/2, that's rad 4 times rad 4 times rad 4. Well, that's, again, 2 times 2 times 2, that's 8. Put the 0 in, you get minus 0. And then there's the minus 1 coming down. I'll turn it red. What's 2/3 of 8? Well, it's 16/3. Minus 1 would be minus 3/3. 3/3 is 1. And you know what 16/3 minus 3/3 is? Oh yeah, you do. It's 13/3, or 4 1/3. So again, my point here is to show you that there's plenty of flexibility and creativity is encouraged. The very first way that I did was by far the hardest, most tedious way. That's the way that usually people will think of first, but I invite you to kind of look around at some of these problems. You might be able to save a lot of time and a lot of effort if you just kind of become creative a bit. So, all right, one more problem and we're done with section 7.1. Number 5, coming your way. So far I've done a lot of my work without a calculator, but sometimes you just have to have one. Normally you'll have a calculator for this, and sometimes the curves just don't cross at a good spot, like here. Check out these ugly points of intersection. Blah. Okay, so you do second calc intersect, and again, our answer needs to be correct to 3 decimal places, so it's important to stay super accurate with your points of intersection, because you're going to be using those to integrate with. Don't round off until the very end. All right, well, the good news is at least it's going to be blue minus green the whole way, and we're going to stay with, y equals, and we're going to stay with x's and dx's and x limits in our work. So I just have to get this set up, and then we'll pop it into the calculator. All right, there it is. Anytime you put something into the calculator, you want to write down what you put in, because if you slip and you fat finger a key or miss a button or just type the wrong thing, your answer is going to be wrong, and that's all you're going to have on the page. And I won't know if you know anything. So at least show me that. At this point, pop it into the calculator and just give a final answer and round that final answer off to a minimum of 3 places. Notice that my limits of integration here, I've rounded off to 4 places when I wrote it down. You can round it even off to 3 places when you write them down, but behind the scenes, I still have them all the way accurate out to as many places as I can. Because again, I don't want to fumble around with the final answer and have that be wrong. So, speaking of the final answer, it comes out to 34.616979778. So we'll accept either 34.616 or 34.617 square units. Remember, College Board will allow you to either truncate, which is the 34.616, or since it's 6169, you can round up to 34.617. That's actually what I did right up here. Oh, look at that. And so we know we're good. And if you look at the drawing, 35 units looks believable. If you really have time left over, you can sit and count blocks one by one and see if you're close. All right, that concludes section 7.1, area between 2 curves.